Welcome back to Logic, Language and Information. In this lesson, we will define the notion of validity for arguments and show how to use truth tables to test for validity. In the following lesson, we will discuss the subtler task of extracting out the logical form of an argument expressed in natural language, as well as the stronger property of soundness for natural language arguments. So let's begin. Arguments connect a collection of premises to a conclusion. One of the key things we want to know about arguments is which ones are good and which ones are not so good. As logicians, in particular, we are interested in what makes the difference between good and bad arguments. The key concept here is that of validity for arguments, which is defined as follows. An argument is valid if and only if, whenever the premises are all true, the conclusion is also true. For an argument with premises A1, A2 up to AN and conclusion B, we will write A1, A2 up to AN double turnstile B to express that such an argument is valid. When sigma is a set or collection of premises, we will also write sigma double turnstile B to express the validity relationship that whenever all of the premises in sigma are true, then B is also true. This makes sense even when sigma is an infinite set, but in practice we will deal with finite sets of premises. Now, it's not just a coincidence that we use the same double turnstile symbol that we used for the logical consequence relationship in section 1.3.2. It is exactly the same truth transfer relationship. Validity requires that there be truth transfer from the premises A1, A2 up to AN to the conclusion B. As noted before, for logical consequence and for true material conditionals, truth transfer does not in any way require falsity transfer. So in any case where one of the premises is false, there is nothing further to check, as we then don't care about the truth or falsity of the conclusion. Equivalently, an argument from premises to conclusion is valid exactly when it is impossible for the premises to be all true and at the same time the conclusion be false. The semantic version of a result called the deduction theorem expresses the relationship between validity of arguments, logical consequence, and the corresponding conditional being a tautology. The argument from premises A1, A2 up to AN to conclusion B is valid if and only if the conditional with the antecedent consisting of the conjunction of A1, A2 up to AN and consequent being B, if that conditional is a tautology. And this is the case if and only if the conjunction of A1, A2 up to AN has B as a logical consequence. When sigma is a set of premises and A and B are formulas, we can write the deduction theorem more succinctly. Sigma together with A yields B, or the argument from sigma together with A has as a consequence B, if and only if sigma yields A implies B. In words, the argument with premises sigma together with A and with conclusion B, that argument is valid if and only if the argument with premises sigma with conclusion A implies B is valid. Let's work through an example of using truth tables to test for validity. Consider the argument with two premises. The first, P and not Q implies R, and the second, not R, and with the conclusion, if P then Q. 3 atomic propositions, so 8 rows of the truth table. If you were doing this problem from scratch, you would have to calculate the truth values of each of the two premises and of the conclusion. But to focus here on validity, we've jumped in and done the evaluation for each of the three formulas already. Now for validity, we have to check the rows of the truth table in which all of the premises are true, but only these rows have to be checked. In this example, the first row, the third row, and the seventh row are the only ones in which both of the premises are true, 1 and 1. In each of these three rows, we must check that the conclusion formula also evaluates to 1. The first row, the third row, and the seventh row. Check. All done. The argument form is valid. Here's the solution with these three crucial rows of the truth table highlighted for emphasis. We first identify the rows in which the premises are all true, and then just in those rows we must check that the conclusion is also true. Conversely, in order to conclude that an argument is invalid, we only need to find just one row in which the premises are all true, but the conclusion is false or 0. And then we stop with evidence of invalidity. In this example, there are 5 other rows of the truth table that we can ignore because one or the other of the premises is false on each of those rows, so they do not affect validity. Now it's your turn to try. Using the completed truth table as shown, test the validity of the argument with 2 premises. The first, not P implies Q, and the second, P implies not R, and with conclusion, Q implies R. How did you go with this exercise? For this one, we can identify 4 rows of the truth table in which the 2 premises are both true. The third, the fourth, the fifth, and the seventh, which have been highlighted for emphasis. Checking these in turn, the third one gives us failure of validity because there the conclusion, Q implies R, is false. We get the 1, 1, 0 pattern across the row for premise, premise, conclusion, and so fail. We could just stop here with a verdict that the argument is invalid and not bother checking the other 3 rows. But we will just to get some practice. The 4th row has the pattern 1, 1, 1 for premise, premise, conclusion, so it doesn't present a problem. Likewise, the 5th row, 1, 1, 1, so again, no problems. The 7th row has the bad pattern of 1, 1, 0 for premise, premise, conclusion. So it also demonstrates the invalidity of the argument. If you have any questions or queries, look first in the course notes and then go to the discussion boards, and I'll follow the postings there. This brings us to the end of this lesson on the validity of arguments, which we now know means that the conclusion is a logical consequence of the conjunction of the premises. And this, in turn, is the same as having the argument conditional be a tautology, where the argument conditional has the conjunction of the premises as its antecedent and the conclusion as its consequent. We have seen how to use truth tables to test for validity, and it only requires checking of the rows of the truth table in which all the premises are true. The next lesson, titled Argument Forms, Instances and Soundness, will examine the subtler task of extracting out the logical form of an argument expressed in natural language, as well as the stronger property of soundness for natural language arguments.